means we need to start. Thank you. So, we're talking so much about glaciers last time. We didn't get done with what I wanted to get done with. That's cool, because I was planning on taking this time anyway. So there. So, we are going to finish up talking about hill slopes and, well, at least mass diffusive transport on hill slopes. Because next week we'll start getting into landslides. But this week we want to finish up with what's up with diffusive processes. What kinds of things what kinds of things can we infer, et cetera, et cetera. So, you will recall that last time we did a mass balance for an arbitrarily deep column of mobile material, and not going to recap all of that, but you will recall we had some slope like this. We drew boundaries on either side. We said, this stuff is arbitrarily deep, say something like a moraine or just a huge pile of wet sand or something like that. We've got fluxes in this way, fluxes out that way, and we did the mass balance and got to the point where we could say that the change in elevation with time, per time, was equal to, well, we had this sort of 1 over bulk density term. That's a lousy U. And then we had the term that was the change in the flux per width. And this was a mass flux with change in distance. Okay, and that looked like this with the curly D's and all that I talked about, the partial derivatives, time on this side, space on that side. So that gives us the changes in elevation with time. So the rate of elevation change is equal to -1 over this bulk density. And again, the change in mass flux per change in distance. So that's where we got to last time, and I said, okay, well, but we spent Monday talking about what Q is. All right, we talked specifically about frost heave, how, well, does anybody remember? So let's see. We talked about frost heave. So we've got the various processes that lead to Q. So we had frost heave, sometimes also called frost creep. Help me throw some out. What do we got? Rain splash, what else? Gophers, yeah, so okay, animal burrowing. It's not just gophers, we gotta actually, maybe account for ants and worms and all that. And we said tree throw also. And, I suppose it's possible that there could be, I'm sure there's plenty that, that can lead to diffusive transport that's not on this list, but this is a decent list to start with anyway. And we showed, or I showed you that that when we look at frost heave, that is the sort of repeated expansion and falling of the soil due to heave pressure in the soil, making ice, growing ice lenses, expanding it, and then when the ice melts, it falls straight back down, that we had a mass flux that was proportional to the negative of the slope. Oh, wait a minute. Forgot a crucial term there. My diffusivity. So mass flux is positive if we're going downhill, hence the negative sign. If we're going downhill to the right, towards positive x. We've got our felt density and our diffusivity or diffusion constant. Here it referred to in different ways, it means the same thing. And we talked about in particular what goes into that in terms of frost creep. More freeze-thaw cycles, deeper depth of frost in particular, greater strain as a result of frost. All those things will lead to a larger diffusivity and hence a larger flux given the slope and the bulk density. With rain splash, bigger drops, more rain, more animals, earlier, stronger animals. Again, we can think of the things that are going to make diffusivity larger. The important thing is that now we've got here something that we can substitute into here to get rid of one of our variables there. And so if we substitute that into our diffusion equation, then we get, well, I didn't tell you, I should have told you, I think I mentioned last time that it was going to be a diffusion equation. It's not really a diffusion equation yet until I write it how I'm about to write it. So let me just go ahead and be real clear about how this is working. So go ahead and pull out my d by dx and put my q in here. Oh, now I got to make my d's curly. Okay. So the negative sign, the density, the diffusivity, we're going to have been assuming that those things are constant, that we can pull them out outside of derivatives. And in that case, the densities cancel, the negative signs cancel, and we end up with a nice, neat, and tidy equation that simply says that. And that is a diffusion equation where what's diffusing is elevation. So what's this say? Well, first of all, let's remember what dz dt is. Okay, so this is saying that the change in elevation with time is proportional to, well, is equal to the product of this diffusivity and topographic curvature. All right, let's deal with, we've talked quite a bit about diffusivity already, but it's worth just a bit of dwelling, I suppose, on what this term is on the left-hand side and what this curvature term is. Okay, so the dz dt, all that is erosion or deposition. So if dz dt is less than 0, then that's erosion. If dz dt is greater than 0, that's deposition. All right. And that's really all there is to that. It's just change in elevation with time. And so now we know that what we're saying here is that the erosion or deposition rate, depending on the sign, is proportional to the topographic curvature via this diffusivity. So, what about curvature? You know, what's this thing? So curvature I'll write it up here again with straight back ease. So what's this saying? This is the same as d by dx of dz dx. So one way to think of it is it's the slope of the slope. Another way to think of it is to go ahead and figure out, well, what are its units? Well, d by itself doesn't have units, so I've got length over length squared, so units of 1 over length. Okay, so curvature as inverse length. What is that length then? I mean, I'm not saying L, that's just a dimension. All right, let's, well, what this is curvature is the inverse of radius of curvature. Let's go back over here where I've got a bit of room. I'm not going to just stop trying to cram things over there. So let's think about that. If I've got a ridge top, let me make it even more extreme here. So if that's my ridge top, I could draw a circle that takes that top in, and the radius of that curvature would be r. And so if I have a small radius, what's that mean? That means curvature is 1 over r, so curvature is large. If, on the other hand, I've got a broader ridge top and therefore can draw a bigger circle, and I have a larger radius, r, so large r, try spelling words. So large r, 1 over a large number is a smaller number, and so large radius of curvature means small curvature. It's worth spending another minute on curvature in order to make sure we understand the sign of it. So let's say I've got a ridge top. Well, the slope of the topography is just the slope of a tangent, right? So as I'm going along on this slope, I'll draw my tangents in there. And what I can see is that the slope is decreasing, going even from positive to negative as I go over the hilltop. So convex means negative curvature. That is, go ahead and write the math up again. Okay, so for convexity, this is less than 0. It's negative. For a concavity, we start with a negative slope. It gets bigger, goes past 0, gets positive. So a concavity means positive curvature. That is e squared z dx squared is greater than 0. Okay? And, you know, we can, it's worth remembering this, especially if we're talking about, oh, this has larger curvature. Oh, well, I mean, you know, larger magnitude curvature, right? So strictly speaking, I have to say, well, I'm talking about a convexity, so it's larger magnitude of curvature, and similarly here, a small magnitude of curvature for the broader slope. And strictly speaking, these are negative, and so, all right. Now, what that's saying then, oh yeah.
Does this equation only kind of work at the top of hills or at the bottom of hills? Because what if you're only taking the mass balance on a slope where there's lots of elevation above, lots of elevation below? Wouldn't the elevation at those areas kind of be the same you would expect, because you have the same amount going in from the top that you have going out from the bottom? So the elevation isn't changing, maybe just the material that's in it is?
I was very sure I caught all that. So I guess let me get back to the first part of the question. Is this only useful at the ridge top or at the notch of the ravine bottom? And let's say, first of all, well, it sure is easier to see the curvature there in those two places. Because, and I've been doing this, I've got a schematic I'll put up in a few minutes, but sometimes it's hard to see when you're off of the peak of it that the curvature is still large. It's just because of the way our brains work and the way we pattern recognize and so on. The other thing I'll say is that this whole business of flux being proportional to slope is good enough in some conditions, not so great when slope gets particularly large. When slope gets particularly large, things, when they start falling, keep going. And so in that case, we can get slopes like we see in the Oregon Coast Range, where they become nearly planar as you get away from the ridge top of it. And there's still a bit of curvature there, but it's less curvature than you would predict, based on a linear model like this. And so you can still, curvature is still useful to your, knowing this from the that linear relationship, saying, okay, this is going to be true at least at the ridge tops, is still quite useful, and I'll tell you why. I think I kind of hit what you needed me to hit there. So what this is saying right here, okay, sharper points erode more quickly, sharper cuts fill in more quickly. Now, provided then we can reasonably, say, infer or assume that over some piece of the landscape diffusivity is constant, then if we can notice or even measure differences in ridgetop curvature, then we can infer from those that that those differences in ridgetop curvature correspond to differences in erosion or overall lowering rate in the landscape. So I want to get to that. Let's just make sure we're clear on these 2 points though. We've got, kind of at the end of the day, we've got that flux is proportional to the negative slope. And that erosion or deposition is proportional to the curvature All right, let me go to some slides. I'll go ahead and start with this one just because I was mentioning the because your question was, what about when you get away from the ridge tops or the valley bottoms? And this is the issue that you run into in places like the Coast Range, where yes, of course I've got this curvature at the ridge top, but my hill slope kind of reaches a 40+ degree slope, and it can't really get much steeper than that and still be a thing. So, it's kind of amazing how steep those slopes are, and they're still soil mantled at all. Okay, here's this looks relatively simple. It friggin' took me forever to get just right. Okay, so what do we have here? This is a simulated scarp evolution according to a linear diffusion law. Okay, so just operating that diffusion equation, starting with a step, and so after like one time step, I think 16 time steps, 64 time steps, so we see that the top of the scarp moves back, the toe of the slope moves out. Okay, what are some key features here? Well, far away from the edge of the scarp at the top, or far away from the toe of the slope at the bottom. In this particular case, in both of those places, the slope is going to 0, the curvature is going to 0, and so the flux is going to 0, and the erosion/deposition is also going to 0. So if it's flat, then nothing's happening according to this model. Here's where the real action, well, in some sense, what we can see as the real action is focused in on these points where, in this case, we've got maximum negative curvature, so maximum convexity, and down here where the arrows are pointing to maximum concavity. And so where we've got maximum convexity, we've got maximum erosion, maximum concavity, we've got maximum deposition. Now, but what if I ask you, well, where is the flux the greatest? Well, of course, flux is proportional to slope. And so where the slope is the steepest, that's where I've got the maximum flux. However, that's also where my erosion / deposition is going to zero because curvature goes to zero. Right? I've got negative curvature here, positive curvature here. At some point, I've got to cross zero. And that's where I do it. So curvature goes to zero there. You know, if I draw a little mass balance there, I've got the same coming in as going out. It's a large amount of stuff coming in and going out, but it's still a net zero change. So, and you know, this is one of those lessons that you can take to streams, to lots of other stuff, right? Just because I've got, say, a high energy stream, doesn't necessarily mean I should get erosion, because erosion has to do with the gradient of the transport. In this case, since the transport is proportional to the gradient, then the gradient of the gradient is the curvature. So at this point, we've got maximum flux, the steepest slope, but no change in elevation. So that's kind of interesting. So again, it's eroding at the scarp top, it's filling in at the toe. All the stuff that's coming off here and going down here is going through that one point, but the elevation right there isn't changing appreciably at this point. Let's see, I think I hit all of it. Any questions on this? This thing took me friggin' forever to get this right. I guess that's good, you know, if I spent forever getting it just right and it only took a little bit of time to go over it, then maybe I did okay. I don't know. All right. So there's one more thing that we can kind of take away from this, is that I'm generally going to expect, you know, if my erosion rate is the greatest where I've got the greatest convexity, that is the sharpest, you know, peak or scarp or whatever, then over time it's going to smooth out. So we can, for example, look at successive generations of glacial moraines. So this is broken top. This is the set of moraines that I showed you pictures of on Wednesday. Here's the Bend Glacier over here and a set of moraines down here. And you can move on out and you can see other sets of moraines that are a bit less well defined, a bit smoother. And so that's actually a pretty reasonable way to estimate at least the relative chronology of moraines. That the oldest ones are going to be the smoothest. They're also going to be the ones that didn't get wiped out by. So generally, we go with moraines. We go from smooth towards the glacier, getting sharper. It's kind of hard not to have that sort of situation. Okay. What other superpower do we have? Well, we can look at a place like this. And if I tell you that all of this has the same lithology, then you can go, well, these ridges sure are, I mean, I can barely see the fact that there are ridges up here. I mean, yes, there definitely are, but boy, that's broad. This right here is a very broad ridge. And over here, at least where there aren't roads on top of the ridges, they're quite a bit sharper. So, again, given that I've told you that the lithology is the same here as it is here, it's reasonable to infer that it's eroding a lot faster here than it is up here. Always nice to look at some other evidence, of course. This is one of our stops on the field trip tomorrow. And this is where that ridge was really broad. This is where the ridge was really sharp. And just from the color alone, we can go, well, this is just a whole lot older. That soils is sitting around oxidizing. and getting redder and redder. It's also 4.5 meters deep as opposed to 20 centimeters over here. Yeah.
Is that Connor in that picture?
I think that is Connor. I didn't want to embarrass him, but I guess he's not here today.
He is.
Is he? No. There we go. Okay. So that's, that's kind of cool. That kind of indicates that, maybe our newfound superpower is actually something of a superpower rather than just a way to make more mistakes. And might give us some confidence to go to some other place, at least in the Coast Range, and go, well, can I say something about what's going on in this landscape, in this part of the Coast Range? I do need to be careful when I get down here. I know I've got Roman noses down here. I've got some intrusive igneous stuff down there, so that's going to mess up my assumption of a constant diffusivity. But actually, knowing that is kind of interesting, right? Right here is Kentucky Falls and North Fork Smith River Falls, right there. And so we know we've got hard points that the stream is not cutting through quickly, because that basalt's much harder than the Tyee sandstone that's everywhere else. So it seems reasonable that as I look up here and I start seeing these broad ridges compared to the really friggin' sharp ones just on the north side of the divide, that things are eroding much more quickly on this side than they are over here. Did you have a question there?
Roman nose.
Oh, it's a place. It's a mountain.
Oh.
Name of a mountain. Yeah, sorry. Yeah, Roman Nose is just the name of a mountain in the Coast Range. It's kind of cool. There's actually columnar basalt cliffs. Yeah. And there's some kind of infrastructure there, so you can actually go and have a picnic, because there's, if you don't mind, sitting next to whatever thing they're doing there. I can't even remember. Anyway. Yeah, so the other thing is, it'd be nice, again, to have some other evidence that confirms, I've told you that, and unfortunately I can't show you pictures contrasting the two, but I can tell you that there is a road along this ridge called Hatzel Creek Road, and as you swing out on the right side, if you're going this way, and you swing out on the right side of the ridge, and you see these hills over here, they look pretty dang steep. It's just when you get to the left ones, they're so steep that you can't see them, because they just fall off so abruptly. You get out here and you see these nice thick red soil beds, not 4.5 meters thick, but relatively thick, where you can see that there's any soil at all when you get a cut on the left side. It's essentially duff on top of gravel. And the gravel is the same color as the bedrock beneath. So there again, very thin soils, not very oxidized, thicker soils, more oxidized. Seems reasonable that our inference based simply on the curvature of those slopes is probably correct. Doing here. All right. Questions?
So it's the curvature of the slope that's determining whether it's eroding faster or slower?
Yeah. Well, it's the curvature of the ridges. I mean, that's what you can really see, and especially on the north side of that drainage divide here, the slopes get pretty planar, pretty close to the top of the ridge.
If it's all the same lithology, what's driving the slope differences between the north side of the ridge and the south side of the ridge?
It's all holding up a waterfall over here, and the waterfall holding up that stream over there. This one's draining up here, goes into Knowles Creek. This is actually the main stem of Knowles Creek up here. It goes into the Siuslaw down by Maple. Over here, North Fork Smith River goes eventually down to the Smith and then down to the Umpqua. The fact that it goes all the way down to the Umpqua is is isn't a huge player. It's mostly simply that, you know, it's stuck on that cliff there, stuck on that waterfall. And you can see it outcropping up here as well. So yeah. Yeah, it's a pretty neat place. It's kind of hard to find, but if you go at 126 and sort of follow the sign that says this way to like Whitaker Creek Recreation Area, but have either really good GPS or really good map, because it's just a maze back there and it's not a straight shot. But definitely, and then it's a bit of a hike to get to the actual falls, but definitely worth seeing, because it's just like, oh wow, two pretty tall waterfalls just right there next to each other. All right. Now, any other questions?
What were the names of the waterfalls again?
Kentucky Falls and just North Fork Smith River Falls, because Kentucky Creek and North Fork Smith River. And like, why don't they're so awesome, why don't they have a better name? Twin Falls or something like that. Okay. Now, turns out there's another bit of mass balance we can do, and this is the one done in the book. We can use this whole diffusion thing to do a mass balance on the mobile regolith part of the weathering profile. And let's see what that can teach us. All right. So all right, so if I've got a slope and say that's the bedrock, and I do have some soil on top of it, all right, so we've got bedrock down here, we've got some layer of soil up here. So we'll take another, just a chunk of this and blow it up, maybe even exaggerate it a little bit for drawing purposes. But now I've got a piece of the slope that has some thickness of mobile regolith. Again, I draw boundaries on my box. I've got soil, so pretty good chance that I've still got diffusive processes. In fact, I'm counting on it. So we've got the usual sorts of flux at the sides. We'll still call the elevation Z. We'll still use our x-axis. But now we do need to be a bit careful with our material properties here. Our regolith here, our mobile regolith, has a bulk density of that mobile regolith for soil that's typically going to be less than the bedrock density, rho sub r. So I've got rho sub b for my bulk density of my mobile regolith, what a lot of people would just call soil, and rho sub r for the density of the bedrock. But if I'm going to actually draw I said I was going to do a control volume on just the mobile regolith part. And it's hard to draw a box around something that's already kind of a box. But you might recall that when I said that I've got this arbitrarily deep pile of unconsolidated material, that I don't need to worry about what's coming in through the bottom. I can draw my box arbitrarily deep as well. But in this case, if I'm drawing my box just around the regolith, the mobile regolith, then I have to account for the input to that box from weathering. So let's draw that in there. I've got a flux in the bottom, and I'm going to call that W dot. W dot is the weathering rate. So let me just put that up here, because we've talked about weathering, but of course, this just has units of length per time. This is the velocity, if you will, of sort of downward velocity of that bedrock mobile regolith interface. But when that boundary moves down, I get material in. Now, I've got to do the mass balance. It'd be nice to just skip to the end, but what I will do is dispense with some of the clunky steps, but I want to look at the change in, I'll just call it soil mass because it's easier to write, for change in time, and that's going to be equal to the sum of the fluxes, right? So I've got the weathering rate, weathering flux. Let me just call that a weathering flux. I've got my mass flux at the, again, we'll call this point x1, this point x2. So I've got my mass flux at x1 minus my mass flux at x2. All right. So let's write this. So mass of the soil is just going to be its thickness times approximately its length this way and its depth into the board. That'll be the volume, and then multiplied by the bulk density, that'll be its mass. Okay. So on this side, and I'm going to go ahead and skip all the way to my curly D's here. I've got bulk density times regolith thickness times a dx and a dy. That dx, I'm shortcutting because I'm tired of going through the steps of saying, well, x1, x2 minus x1 is delta x, which goes to 0, which becomes dx. Okay, so that's that lengthwise increment as things get small. What's that equal? That, again, equals this weathering flux, but it's a mass rate. this is a velocity. So let's see then, for if this boundary moves downward, then I've added some mass of bedrock to my mobile regolith layer. So for this one, I've got to multiply by the rock density. And then I've got my weathering rate, and then the usual multiplied by dx and dy to get the mass. And then, if you don't mind, I just want to skip to over here, except that's going to have to be a minus sign. So we did this before, right? This is the part that's new, that's old, right? That part's kind of different from what we did before. Oh, I can't quite do that, sorry. All right. I'm just going to write it like that, because I haven't divided through by my dx's and dy's and all that stuff. So, all right. Might take more time saving steps writing on the board, but so Q, I've got a differential of Q that is just, you know, Q at x2 minus Q at x1. Since Q, it has units of mass per length per time, because it's a mass flux per unit width. To get a mass, I have to a mass per time, I have to multiply by that with dy. Okay. Now, similarly, as I've done before, we can look and see what can we pull out and divide everything by. On this side, if I just want to make that left-hand side be the rate of change of regolith thickness, then as long as the bulk density is going to stay constant, I know my dx and dy are constant by definition, so I can pull all those out, divide through by all of those things, as long as I divide everything by those things. Right? The dy's all cancel out. Kind of anal retentive of me to put them there in the first place. The rho b's cancel out on this side. Of course, my dx's cancel out. Everything by design cancels out except my r on this side. So let me rewrite that in a way that's a little more pleasing, a little less ugly. So we see on the left-hand side, right, we've got just that dr dt. For our weathering term, we can cancel out the dy's, of course. And the dx is. So my left-hand side, I get that. My right-hand side, I just, again, I cancel out the dx and dy. But I'm left with this ratio of densities. So the rock density ratio with the bulk density of the mobile regolith times the weathering rate. And then over here, I turn this into a derivative. My dy's cancel, but my dq and my dx become the derivative of, a partial derivative of q with respect to x. And I've also got this 1 over rb, rho b, I'm sorry. And so like so. I can do the same old trick because Q equals negative rho b times the diffusivity times the slope. Same as it ever was. And so again, you can see when I put this in there, and I can pull these out, my negatives cancel one another, my rho b's cancel one another, and I just got plus kappa d squared z dx squared. So what this is saying is that the rate of change of my thickness of my regolith is still governed by diffusion in part, but it's also governed by the input due to from weathering. Now, what's that got to do with the price of tea in China? I mean, so what? Well, turns out we can at least look at some interesting cases. Oh my God, did I just run out of time? All right. Okay, in the case where the regolith depth is not changing, what this says is simply that my curvature, geez, sure I get this right. Yes. So if this goes to 0, then my curvature is equal to, or the negative, I'll go ahead and keep the negative sign over here. So that's essentially how sharp my ridge top is equal to the ratio of the densities and the ratio of the weathering rate and the diffusivity. Okay, so what does this say? This says that all else being equal, if I've got a greater weathering rate, is that right? Greater weathering rate, then I'm going to have greater curvature. Did I get that right? Yeah. If I have, let's make sure this makes sense. If I've got a greater diffusivity, this is going to be smaller. My curvature is going to be smaller. So my transport's more efficient, gives me smaller curvature. Anyway, I don't have time to get profound about that, I'm sorry. So this was just sort of as the time allows kind of thing. But it is kind of cool that, you know, the curvature is equal to this ratio of the weathering and the diffusive. All right. See you tomorrow, yes. 8 a.m. in lobby of Wilkinson.
Is there homework this weekend?
Yeah. There's a quiz as usual. It's posted already.
Will landslide stuff be out in the trend?
I haven't decided yet. I haven't decided.
Okay. All right.
Yeah.
We'll worry about it next week.
All right.